am talking about Cuisenaire rods. And I'm going to try to do a very quick overview, but already having done this once, I realize I'm going to have to go really fast. So, Cuisenaire, who uses rods and came up with a children's curriculum, starts out with relationships, and there are lots of staircases like this. If you look, this is a 1 centimeter by 1 centimeter by 1 centimeter. It's white, and you can see that 2 of these equals a red, 3 a green, and so forth, leading one to eventually come to that this can be represent 1, 2, 3, 4, all the way up to 10 for each of the rods. And the reason that I say can is because you will see that they can also represent other things. They're not always the most obvious. So he spends a lot of time in the beginning on staircases and relationships. He has you start with a white rod, and then if you notice, this staircase is built by 1. Each time you add 1, and he starts by, after the 1, adding by 2, which gives us 3, 5, 7, and 9. And then he starts another staircase by 2, adding by 2, which gives us 2, 4, 6, 8, and 10. And he does a lot of notice and wonder. There's a lot of allowing children to discover certain things for themselves. So just to give you an idea, I noticed that all of these are odd. All of these are even. I noticed that they alternate every other one from the original staircase. Both of these do. And that all of these comprise all of this one over here. So he spends tons on relationships like that. A lot of time is spent on that. Then you move on to making trains. A train is anything that you would bring back to back like this. And this train is expressed with a positive. And then when you find out what these equal, this one equals 7, you can see like this, the equal sign. So our green plus our purple gave us black right there. And he also starts out with using algebra instead of using whole numbers. So this can be used for addition. If we take this away, this can be used for subtraction. We can write the same thing as black minus green gives us what? It gives us 4. And we can use this for greater addition. For instance, if we wanted 27 plus 9, then you can trade these to see what we need. Like this and 1 of the 7 gives us 10, and that leaves us with 6. So these can be traded for 16, and I started out with 27, so that leaves us with 36. So it can be, there's a lot of exchanging for an understanding of number bonds, and they do a lot of permutations as well. So if you're looking for number bonds for 10, you know, how many different arrangements can we do for 10? And there are different, they use different challenges for this. How many different arrangements using only 2 rods in a train can we make for 10? So this would give us our number bonds. Well, that is not a 9. My kids have these memorized, but I do not. So 2 and 8, 3 and 7, 4 and 6, and you just keep going along the line. When you have something like this that gives you a rectangle, this is called a pattern with Cuisenaire. Okay, so it can do number bonds or permutations. Permutations are one of those things, you know, you have 3 flavors of ice cream. how many different ways can you arrange your ice cream cone, those kind of things. There's actually a formula. This is where factorial comes in, and you can use these physically to arrange the ice cream cones. And you usually have to look for a logical way of doing this so that you don't miss anything. Like if the whites are up front, and then you would start out with something very small. Actually, I would start out with 2 flavors and then move up, see what the children notice, and see if you can eventually come up with a formula for, because there's an actual formula for finding how many variations that you can get of something. So this would be all of the different arrangements that are available for 3 different flavors of ice cream and stacking cones. So there's permutations. In addition to that, you can look at factors. When you have a train that's all the same color, like this train here, this would be a factor of 10. 2 is a factor of 10. It fits in 5 times. I have 5 2s or 5 red that gives me a 10. We also know that I have 2 5s will give me 10 also. And if you do enough of these with the children, then they will realize the pattern here and understand the mathematical property with addition and multiplication, that it doesn't matter the order that you do them in. In addition to multiplication, I don't even know what to order to go here, guys. There's just so much available. In addition to factors and common multiples, so if you're trying to find the common multiple with 2 and 3, you would just go up by 2s and go up by 3s until you come to the same place, like here, and we know that the common multiple of 2 and 3 is 6. Is division, but the interesting thing, if we look at, let's just look at the 5s and the 10s for now, is that from what I can tell, Gluentno didn't really think division was the inverse of multiplication, but rather the fraction was the inverse of multiplication. Like for division, you can say how many 5s fit in 10, and we can see that 2 5s fit in 10. We could say how many 2s fit in 10. We can see that 5 2s fit in 10. But if 10 is twice as big as 5, then 5 is half of 10, and that's a really easy concept for kids. It's a little bigger jump when you say if orange is 5 times greater than red, then red is 1/5 of orange. And eventually on some of these, and if you've been watching my fractions, you've seen some of this work already, you'll catch something that doesn't fit evenly. Like 8 is not a factor of 10. And where you move from here is going to our whites or our reds, finding something that is a factor that does fit evenly into 10. And as we know, our whites do, so do our reds. And you can find both equivalent fractions in this activity, as well as determining what this fraction is equal to. So if 10 is 10 times greater than this 1, and this 1 is 1/10 of this, then this 8 is 8/10. Or you'll see here, remember our reds are 1/5. 4/5 of 10. So it goes through fractions, goes through permutations. You can also use it for square numbers. This is like one of the first activities in every child that I've seen that uses Cuisenaire rods is building of a pyramid. And what they notice in building the pyramid is that you have to have the same number of rods for whatever rod you're working with to make the square. So 5 5s, 4 4s, 3 3s, and so forth. So you can use this for both discovering square numbers and also for understanding roots. Like, you know, for finding square roots, say you have 25 and this needs to make a square. So how do we arrange that? How do we make a square? Okay, I'm looking at this and thinking I better do this in 2 parts because I'm already at 11 minutes. So we'll do a part 2.